Hello, welcome to the second Tom Rocks Maths live stream. So this will be the same as one last week if you were here. If you weren't, the idea is I'm going to start with some questions that have already been sent to me, which are based on the travel graphs video that I released on Monday for the Tom Rocks Maths Appeal GCSE high school level maths series that we're doing. So I'm going to start with some of those questions. We'll start off reasonably simple, and then we'll get on to more advanced topics because they're the most interesting. They're the ones I enjoy the most. I'm sure we all do. And then after that, there should be some time left at the end for everyone to ask questions in the live chat. And then I'll pick some of those and we'll talk through some of those towards the end. So the whole thing will be about an hour, again, similar to last week. And we'll see how it goes. I've updated a few things. So I now have a microphone attached to me. I don't know if you can see it. So hopefully the sound will be a bit better. And hopefully the technology won't crash halfway through, which also happened last time. So I've jinxed it by saying this now. So let's kick off with a question. So this one came from, this kind of came from two people. So Ryan asked, could I talk through some more of the graphs from GeoGebra? So if you don't know what I'm on about, you need to go and check the description part of the video from Monday. So the Tom Rocks Maths Appeal video on travel graphs. In the description, we gave a link to a GeoGebra interactive resource where you can plot travel graphs, and then it shows little cars sort of acting out what the travel graph is displaying. So Ryan asked me to do some more of those. So I'm going to take some more examples from there. And obviously, you should join in and do these yourselves at home. I'll tell you which particular graph to click on, which number it is. And then also David asked us the question was, how do you work out what is happening from any given travel graph? So if you just get, travel graph is thrown in front of you, how can you actually see what's going on there and what the story is and how all of these different people, cars, whatever they might be, how they're all interacting? So I figured I could answer David's question by also using examples from GeoGebra to keep Ryan happy. So hopefully this will make both of them happy. And hopefully you're also watching. If you are, hello, David and Ryan. Thanks for your questions. So the first one I'm going to do, like I said, this is from GeoGebra. So the graph looks as follows. We've got the usual, we're going to have time on the x-axis and distance up here. Of course, these can be any way around. There's no reason they have to look like this. This is just what we did in the video, so I'm going to try and be consistent. So we've got distance on the y-axis, time on the x-axis. And the graph, first one we're going to look at, I'm going to get some different colors, is going to be, there is a blue truck, which is going to do that. Okay, and then there's going to be another, this is going to be a motorbike, which is in red, which is going to do that, that, and that. Right, so this is velocity 6 on GeoGebra, if anyone is currently on GeoGebra trying to figure out what's going on. So now the question is, what's happening? So this was David's question. We've been given a travel graph, and we want to interpret this and figure out what might actually be happening here. So, for example, let's start with the blue line. So just focus on the blue line. That's this straight line here. So let's ask the audience, right? Let's ask you guys. So I want to know, if you let me know in the chat box, what do we think is happening for the blue truck? So the blue line, what is that truck doing on our road, right? So if we had our road over here, like the GeoGebra example. So what is the truck doing based on the graph? I will eventually explain if no one answers, but I want to wait. Yes, perfect. Thank you, Sam. Blue is moving at a constant speed. Exactly. So blue is just a straight line. The gradient is the same throughout. Well, it's me attempting to draw a straight line. And yes, as Sammy says, is moving uniformly. So the truck is just moving along at a constant speed along our road. Now, the bike in red, what is the bike doing then? if the truck is moving at a constant speed, what is the bike doing? So there's kind of 3 sections to the graph. We've got something happening at the beginning, then something slightly different because the gradient's changing, and then something happening again at the end. Right, so blue, I don't know how I can really draw an interactive picture, but we've got a truck sort of starting here, moving at some sort of constant speed along the graph. Now, what's the red one doing? Right, exactly. So thank you, Nar, and No One's Perfect. The red bike is starting to move faster, right? So the bike's going at the same speed as the truck. So happily, so the bike's kind of starting. How do you draw a bike? I don't even know. I'm just going to do a circle. Can't really draw a bike from above. So you've got a bike, and this is moving at the same speed as the truck to start with. But then at this point here, it goes faster because the curve's steeper. So the bike's going to accelerate. The bike's, I guess, drawn by like 2 arrows. It's going to overtake the truck, and then it's going to move back in front of the truck and carry on at a constant speed. So the story of the graph, to answer David's question, how do you interpret these graphs exactly for what's happening? They're moving at the same speed to begin with. Then the bike, the rider on the bike has clearly decided, I'm not happy going at this speed, I want to go faster. So has decided to overtake the blue truck, therefore has sped up. It passes the blue truck here at this particular time. And then the bike is ahead of the truck, gets a safe distance ahead, and then returns back to its normal speed. So this graph is basically showing an overtaking maneuver happening on the road. So let's try another one. So as I said, if you want to play with this yourself, this was velocity 6 on the GeoGebra resource. So you can click on that and you can like see it happen in real time. Instead of my terrible pictures, you can actually see these things animated and see these things move. So let's now, could have kept my axes, look at a slightly different one. All right, well, rub them all off now. So let's look at the following. So there's only going to be one car this time, and its distance time graph is going to look like that. So now I would like you all to have a think about what is the car doing. So I want you to tell me the story. We have a car on a road, and I want to know, what is the car doing? Is it accelerating? Is it overtaking? Is it reversing? Who knows? So using the graph, you should be able to tell me the full story and the full description of how this car is driving along the road. Excellent. Thank you, Chandana. Chandana? I hope that's saying that correct. Probably isn't. Does this mean the car reverses and then stays in the same place and then moves again? It does. Well done. It means exactly that. The car is starting at a constant speed, driving along. At this point, then for some reason decides to reverse. Then it stops because the graph is going flat. So I should have labeled my axes. Terrible mistake. So it's going flat here. The distance isn't changing. And then it decides to speed up. So maybe like we can make up a pretend story and say that the car was driving along with, let's say it had like a suitcase strapped to its roof, and then the case falls off. So the driver realizes that the case has fallen off. So they stop, they then reverse, then they don't move whilst the driver gets out, picks up the case, puts it back on the roof, and then they carry on with their journey. So you can have some fun making up these stories, actually. Like, these would be pretty creative exam questions, like tell you a nice, beautiful story about losing a suitcase, and you have to draw the graph. Right, so we'll do one more of these, because I found another one as an example. And I should say the one I just did, the second one there, that is velocity 4 on the GeoGebra interactive resource. So I will also post a link to that. Actually, I should probably put the link to that in the chat. Let me do that. So if anyone wants to have a go, then they can. Right, okay, here we go. Right, there is the link to the interactive GeoGebra. So now you've all got that. So we did, first of all, we did 6. That one was 4. And now we look at one more. So this time, it's going to look like the following. Distance again on the y-axis, time on the x-axis. And what's going to happen this time is going to be a car. It's going to go, actually, let's use different colors. So there's a truck in blue. There's going to be a bike. Let's do the bike in red again. And then there's also going to be, I think the green was a convertible or a sports car. So we've got a sports car in green. So what is happening in this graph? Anyone got any ideas? I'm aware, in case you hadn't realized, there's obviously a delay between me speaking and then you guys seeing what actually happens. Right, amazing, okay. So the truck is stopped, yes, and then the 2 cars are moving opposite, and the origin is in the middle of the road. Exactly, I think. We pretty much got it, right? So you've got your convertible and your bike. So if we draw the road, what's really happening here is there's your truck in the middle. Let's say the truck was here, shall we? And your truck doesn't move because it has a flat line. So the truck's distance doesn't change at all. Now, the red one is going to move the bike. Whoops, it's on the wrong side of the road. Drawing everything on the left because I'm in England. So you've got a red bike here, which is moving like that way. And then we've got our green convertible. It's going to be up here, moving that way. So what's happening is the truck isn't moving. So let's say the truck's broken down. So the bike obviously wants to go around the truck, but the bike hasn't looked and hasn't seen the convertible coming. And so the bike has moved into this lane and then they've crashed because 3 of them are staying still in the center of the road. So they're all stuck here and there's a big crash at the X. So it's kind of like the one we did in the video with the ambulance. So we could also, if I wanted, we could then have, once they've crashed, you'd have an ambulance coming in, picking everybody up and then driving away, like we had in the example, the last example we did in the video. Right, so thank you, Ryan, and thank you, David. Those are both questions. I hope I've addressed each of those for you. So now I've got another sort of combination of questions. So Lewis asked, what would the travel graph look like around a racetrack? Which I think is a great question. So I'm going to address that one. And that also fits in with a question from Prasik, who asked, what does a travel graph look like when the speed isn't constant? So I'm going to show you the travel graph for a lap around a racetrack, and that will include parts where the speed isn't constant. So I can do both questions together. So I'm going to do a made-up racetrack now. So I'm going to draw something random. So you have a chicane. I'm going to kind of have a loop there. I'm going to come around like that. Right. This is my made-up race circuit. Let's call it the Oxford racetrack. And you're going to start here. So this is the start of the lap. And we're going to move in that direction. And now what we want to do is think about what might a travel graph look like if we were to drive around this circuit doing a lap. So we're going to need our graph. We will do distance on the y-axis again, and time on the x-axis. Okay. Now, at the very beginning, let's suppose that the race is just starting. So at the very start, we're going to be still for a short period of time. So we're going to be flat down here. And then the green lights are going to come on, and we're going to start the race. So we begin by accelerating. Now, before on our graphs, we only showed a constant speed, and so that was represented by a straight line. But if there's an acceleration, what's happening is you're starting here from 0 speed, and then you're gradually getting faster and faster and faster. So there's like a gradual change, a gradual increase in your speed. So you don't just suddenly go from 0 to some angle, some speed. You have to get there gradually. So you get a curve rather than a straight line. So what you kind of see is something like this. So you have this curve shape as we start to speed up. And then let's suppose we get to top speed before we get to the corner. So we've reached our top speed, which is going to be this line here. So we accelerate, we reach top speed. And now we're approaching the corner. So the first corner, we're going to have to slow down. And this is actually quite a sharp corner. It's like it's a full U-turn. So we're going to slow down quite a bit when we go around this corner. So this, again, like we sped up at the start gradually, we're going to gradually slow down. So this will become a bit flatter. Now, it won't go completely flat because we're still moving. The car is not going to actually stop as we go around the corner. We're going to keep moving a little bit. Hello, a human being 22. So we're going to not stop, but we've slowed down. So now we start to go a bit flatter and we go around the corner. And as we leave the corner, sort of here, we're going to speed up again. So we speed up a little bit and then we approach the corner again. So we're going to have the same behavior as we saw here, the slow down and then the speed up as we leave the corner. So we're going to flatten off a bit and then speed up again as we leave the corner. So if I sort of try and match up the graph with the circuit, we've got this corner here is this slow down and speed up section. This little sort of hump shape, like S shape almost. And then we have the second corner, which is there. And now we're going to have, again, the same thing, the same slow down, deceleration, and acceleration. Oh, getting tangled in my wire. So this will slow down a little bit, and then we speed up. So again, the same kind of bump in our curve. And that's going to be our third corner, which is going to be this one. Now, we're going to, again, accelerate and reach our constant speed. So that's going to be our straight line going at our top speed. And now we're approaching another corner, but this is less sharp. So these first three were all U-bends, so they were really quite slow. So here we're going to have to brake a little bit, but you're going to take this at sort of 75% speed, let's say. It's not really that sharp of a corner. So what we're going to do is we're going to slow down a little bit, but then kind of take that through at 75% speed. And then as we come out of the corner, we're going to probably still be going about sort of 75% speed until we sort of get down here when we start to really accelerate again. So there's going to be a decent chunk where we're going at not quite top speed, but quite fast. And then we're going to accelerate. I'm running out of board space. And then we're going to accelerate to top speed. And this is a really gentle corner. So we're going to just go at the same constant top speed all the way back until we cross the finish line. So the last part, if I could draw it, let's just pretend it continues down here, will just be top speed in a big straight line because we have this nice gentle final corner. So if I redraw that so that it all fits on the graph, just do that again so that we can see the full lap as we go around the circuit. So this is time. Right, so we were flat, then we accelerated. So oops, there's a curve. Then we had our first corner. So we said that was this sort of bump shape. Then we had our second bump shape. Then we had our third bump shape. Then we went to sort of a little bit slower than 75% speed. And then we finished with a steep part. Okay, so we've got first corner, first U-turn, second U-turn, third U-turn. This is like the fast corner. And then this is the home straight. So again, going back to the first question I looked at and David's question, which was asking, can you always interpret the travel graph to see what's happening? So if we didn't have the circuit, so if I just didn't show you the racetrack, given this graph, you can still figure out what the racetrack must look like. So just given the particular graph, so you know there's a deceleration followed by an acceleration. So there's a corner. There's another corner where there's a bump. There's another corner. Here, as we've seen, there's a slightly faster corner, and then there's the home straight. So you can figure out all of these things without actually knowing what the racetrack looks like, which is quite neat. All right, so that was concentrating on Lewis's question, which was to say, what does a travel graph look like for a racetrack? But I also mentioned that Pratik had asked about what happens when we have non-constant speeds and when we've got acceleration happening. So what I thought, so I've shown some examples there of acceleration and deceleration where we get this smooth curve. So what I thought would be useful was to sort of talk through properly how we define the gradient of a curve rather than just a straight line. So I will rub this off and then we will get stuck into that. And that'll be the final question that I've got sort of prepared, and then we'll open it up to any questions in the chat. Right then, so we'll start by looking at, this is going to be Usain Bolt's. So like we did in the video, like Bobby did, this is Usain Bolt's 100 meters world record. So we've got the graph as follows. We've got, this is distance again. This will be time. So we know his world record is, I think it's 9.58. Someone I'm sure can correct me if that's wrong. And he's going 100 meters. Now, so we've got to get to this point here. Now, the graph Bobby showed us was the very, very beginning. And then there was an acceleration as he started to speed up. Then there was this period in the middle of sort of constant speed. And then towards the end, we saw a little bit of a tail off in the speed. So it's not quite as flat as I've drawn, but it's sort of certainly slowing down at the end. So again, it's kind of like a flat S shape almost. Now, if you watch the video that I released earlier today, which was Bobby explaining this graph in more detail, he actually told us that this section in the middle, between 30 and about, so this towards the end is about 70 meters. So this section in the middle is where the sprinters are really powering through. So this is where there's sort of an acceleration at the beginning. They build up their pace. Then they power through at their absolute maximum top speed, which I think is about 26 miles an hour or so for Usain Bolt. Incredibly quick. And then you start to slow down a little bit towards the end for those last 30 meters. Now, if we want, so this would be an example of a distance time graph where there's a non-constant speed. Now, if we want to know the speed at certain points in this graph, so if we want to know the speed in the middle section where the sprinter is at their top speed and is powering through, then you basically just need to know the gradient of this straight line, because this is approximately a straight line in the middle. They can maintain this top speed for about the middle 40 meters. So here, all you do is you just figure out, you turn this into a triangle, and then I think the method that you're possibly taught at school is you measure these two y values, these two x1, x2 values, and then you can say that the gradient is equal to the change in y, so y2 minus y1, divided by the change in x. And so hopefully you recognize this formula. This tells you the gradient of a straight line. And you have these 2 points, y2, y1, x1, x2, like I've drawn in the graph. Now this works for this middle section. This is completely true, and this will give you the maximum top speed there, which, as I said, I think is about 26 miles an hour for Usain Bolt. But now what we might want to know is, well, what is the speed here? Let's do this in a different color. You might want to know what is the speed down here at this point of the graph. And now this isn't as easy because this isn't a straight line, so we can't really use our straight line triangle trick. So what we have to do is as follows. We have to, I'm going to start by drawing a bigger graph. Let's do that. So put it over here. So we want something that looks like that. So we've kind of got, so this start piece kind of looks like this. And I want to know what's happening in this middle. So I can see somebody just said we do the tangent, which is completely correct. Well done. So by the tangent, what we do is you take your ruler or your straight edge, whatever it is, and you draw a line here, just touching the graph. So again, this is something Bobby mentioned in the video. You draw a line just about touching the graph at this point so that the angle on both sides is about the same. So we're making an estimate, but it's pretty accurate, right? You want to know the gradient here. You draw your straight line. Now you've got your straight line, and so you can go back and do your triangle method. So you would just then draw in your triangle like so, and then you can work out the gradient using this formula, right? And that gives you a very, very good estimate of the gradient at that particular point. But if we want to know this exactly, so we want, we're mathematicians, we don't want to just guess things, you want to know the exact answer. To get the exact answer, you need to use differentiation. And I don't know if you've studied this yet, but certainly isn't studied at GCSE level, which is what these are primarily pitched at. But it kind of works in the same way as the gradient formula. And I'm going to convince you sort of how that works now. So if I, first of all, let's rub off this graph, because we're just focusing on that first part now to try and get the gradient there. So and I should also mention, even if you have studied differentiation, I will hopefully present it to you in a slightly different way and explain why it works. So what we've got is the following. I'm going to, as I said, I'm just going to focus on this curved part of the graph, this acceleration at the beginning. So what we can do is draw a really big picture of it. And then I'm going to call this is going to be y equals f of x. So my variable down here, of course, is x. And I'm just saying that on my y-axis, I'm plotting a function of x. That's all this notation means. So I've got f of x, and I have x. Now, if we then want to know the gradient at this point, let's say here. So we want to know the speed, which is equal to the gradient of the graph at this point. So what we do is kind of try and follow our triangle method. So you can say, right, well, if I extend a little bit that way, just make this a bigger axis. So if I just draw a straight line here, I'll do this in red actually, draw my horizontal line, and then I can then draw up a vertical line until I get to my graph. And now, if I join these 2 points together, this line here is pretty close to the white line. It's not exact, but for now, it's sort of what we were doing, very similar to what we were doing over here. We're taking an estimate. We're just drawing a line that looks very similar to the slope of our white line, and we're going to try and work out the gradient of that line. So if we were doing that, so this value here is at the point, let's call it x. And then this point here is going to be x plus some number h. We don't know what h is. We don't really care. It's some little extension across, right? So this is x1 and this is x2 based on our notation that we've used there for m. And then if I then go across to here, this point, so our value is x, and this is given by y equals f of x. So here, the value is f of x1. And then here, y is equal to f of x2. So now if we plug these into our formula, we get that our estimated for the gradient here is going to be f of x2. So this one, remember here, this is y2 and this is y1, again, for our formula. So we've got f of x2 minus f of x1 divided by x2 minus x1. So this is exactly the same formula as we've got in this equation here, but I've just expressed it in terms, instead of using x1, x2, y1 and y2, we actually know y2 is f of x2 and y1 is f of x1 because we're at this point, which is still on our curve. So we're now back to a formula that we are familiar with. That will give us an estimate. It's going to be sort of accurate, but not perfect. Now, what can I do to my diagram here to make this estimate better? That's the question. So I'll give you a bit of time to think about that. So we have this particular estimate at the moment based on this picture. And what I want to know is how can we make this red line even closer to our white line? Because we want to know the gradient at this point exactly. Well, we are going to differentiate, Sam, but we're trying to get there from the geometry. So what can I change about my picture to make it a little bit better? There we go. Awesome. Right. GR has said, move the points closer. That is exactly what we want to do. So if instead of going across to this point, I had just gone across to here and then gone up. So now the blue triangle, and then I draw my straight line. This blue triangle is much closer to the white line than the red triangle. So the blue one is much, much better. It's a better estimate. So instead of doing x plus, our original one was here, which is x plus h1. Now we're at this point, which is going to be x plus h2, where h2 is smaller than x1. And we can keep repeating this process. So if we were to go again, my diagram is going to probably get very unclear now. But if we were to go again in green, like that, the green triangle right in the center is now even closer to the gradient. And we can just keep doing this. So what we're doing is we're getting closer and closer to our point here. Now, to think about what that means, just remove this one. So we started with x2 equal to x plus h1 and x1 equal to x. So if I substitute those into this formula, this is actually equal to f of x plus h minus f of x divided by x plus h minus x. So all I've done here is took the fact that x1 was just x and x2 was x plus h1, wasn't it? Sorry, x plus h1. Now that's going to simplify a little bit. So our gradient m is in fact going to be f of x plus h1 minus f of x divided by, these x's will cancel, and we have a h1 on the bottom. So what happens now when we consider the blue triangle, which we called h2? So we have the same formula. So let's call it m2. This one can be m1. So m2, f of x plus h2 minus f of x divided by h2. And this, remember, is a better approximation than m1. So what do we have to do to this particular formula to make this the most perfect approximation that we can get? So h2 is less than h1, so we want to then take h3 less than h2, h4 less than h3, and we're going to keep decreasing this horizontal distance. So we get closer and closer to x. So we're going to have to take a limit. And what number will we end up with for h? Awesome. H will tend to 0. Perfect. Now, the reason this is written as h arrow 0, yes, exactly, Sam, infinitely small, smaller and smaller. So the reason we write it as tending to 0 is because we cannot let h equal 0, because then we're dividing by 0. And we can never, ever divide by 0, right? You have to take a limit as you go to 0. You cannot just plug in h equal. So what we actually want to do, and this is going to be our final formula, is we can say, if I just call that h, and remember, this is motivated entirely by our picture, just from the geometry. We're saying that the gradient, m, is equal to the limit as h tends to 0 of f of x plus h minus f of x over h, where you take the limit of that entire thing. And that is the definition of differentiation. That's exactly how you calculate the derivative of a function. So let's go ahead and do that. So we started by considering triangles, and then we realized that if we make this point closer and closer to x, we get a better and better approximation for the gradient. And so if we actually take it at x itself, we get the exact answer. So when we do that, we get this formula up here. So let's try and apply it to some functions. So the simplest function I can think of is going to be y equals x squared. We're going to consider a parabola. Right, so if I say f of x equals x squared, my graph is something like that. And we want to know the gradient at some point here, x. Want to know the gradient there. Now, we want to use our formula. So we know that the gradient is equal to f of x plus h. So all you do is you take your x and replace it by x plus h. So this is x plus h squared minus f of x, where f of x is x squared. And then we divide by h, and I forgot to write that we're taking the limit. M equals the limit h goes to 0 of this. Right, so we don't worry about the limit for now. I'm going to just leave that there. And we're going to calculate what's happening in this bracket. So if I expand out this bracket, this will give me x squared plus 2xh minus h. No, whoops, minus 2xh. No, they're all pluses. Don't know why I keep writing minuses. X squared plus 2xh plus h squared. So I expand out this bracket. And so what I've now got is the limit h goes to 0 of x squared plus 2hx plus h squared minus x squared all over h. Now, the x squared is going to cancel. We've got a plus x squared and a minus x squared. So they disappear. And then I've also, now I've got a h on the bottom, but I've got a h on the top and a h squared here. So they cancel. And so what I'm now left with is the limit as h goes to 0 of 2x plus h. And that's it. The h has disappeared from the denominator because it's cancelled with the h's on top. So now I just take the limit. Now I can actually just plug in h equals 0 because there's no h on the bottom. So I'm no longer dividing by 0. It's completely safe. I can just plug in h equals 0, and my final answer is 2x. And 2x is, of course, the derivative of x squared. So this is equal to f prime of x, and this is also equal to our gradient m. So that's an example with an actual function. And I hope that by showing you the geometry of where that came from, you can see why this formula works. And now we can use it. So here we're using it to calculate gradients. But to go back to the initial purpose of why we wanted to do this, remember using this formula up here at any point on the curve. OK, you're very welcome, Sultan Hamid. Right, I'm going to rub this off, and then I'm going to open it up for any other questions we have in the chat. So if you want to ask questions, it can be based on what we just did. If you want me to do another example, give me another function. I'll happily do that. Or if you've got some other questions, that's also fine. OK. What do you get if you integrate a distance time graph? Nice question, Sam. Let's have a think, shall we? All right, so let's take a simple one to start with. So if we had a constant speed, so this is distance, and this is time, and let's just say this was y equals x. Right, so where that would be going, we're going 1y with 1x, so we're going at 1 let's say 1 meter per second. So our speed is 1 meter per second. 1 meter per second, because this is time in seconds, and this is distance in meters. All right. So if we want to now integrate this, then if you think about geometrically what does an integral mean, then it's basically calculating this area. Right, so an integral, one interpretation of an integral is like the derivative is the gradient of your curve. The integral gives you the area underneath your curve. Now, so what are we going to get when we integrate that? Does it make anything sensible to integrate? I'm not sure it has a physical meaning, but if we were to integrate the distance, let me think about this. So we're saying we want to integrate y with respect to x. So that's saying we want to integrate the distance with respect to time. I'm tempted to say it doesn't have a physical meaning. So geometrically, it's the area under the curve. But in terms of like, is that a physical quantity? I don't think it has a physical quantity by just integrating distance with respect to time. So I'm afraid I was hoping that was going to turn into something interesting. I've never thought about integrating a distance time graph. So I suppose the answer would be it gives you the area underneath your graph, but that doesn't really have a physical interpretation. All right, have we got any other questions? Thank you, Vlad, for answering the question about continuity. Been paying attention in analysis, I see. Is there a geometrical interpretation for the integral like the one I just did for differentiation? 100%. All right, let's try that. Okay. So integrating, as I just mentioned, is working out the area underneath the curve. So suppose we have, again, f of x. This is going to be x. So let's think about this. If I do, let's do the same example, y equals x, which is our f of x, right? Y is equal to f of x, which is just that. Right, so if we want to know the area under this curve, actually, I can't really do a straight line because we all, well, we can do this one actually, because you all know, I hope, what this should be, right? So if y is equal to x, then this is, let's call this a point, what can this be? This can be b, and so then this one up here, y is equal to that, so y is b at this point as well. So then what's the area underneath my curve here? So just geometrically, you can hopefully just tell me what the area should be under that curve based on the shape. B squared over 2. Thank you, YOLO. Right. So it's just b squared over 2. It's the area of a triangle. Triangle area is b squared over 2. So, and then if we had integrated our function, whether or not you know how to integrate, but let's suppose you do know how to integrate. The integral of x dx between 0 and b is equal to a half x squared between 0 and b. So that's b squared over 2. So if you don't know what I'm talking about with these integrals, don't worry. But if you do know how to integrate, you'll know that if you do the integral formula, you get b squared over 2. And from the triangle, by geometry, we get b squared over 2. So again, it's a simple example, but it shows us that the integral is calculating the area like we think. Now let's try something a bit trickier. So let's try. So what I'm going to do now is take a general function, y equals f of x. This is going to be x. And we're going to suppose that it looks something like that, right? So it's kind of like a cos or a sine, some kind of curve. Now, as a first approximation, we want to know the exact we want to know the exact area between these 2 points, right? So between 0 and let's call this A. And then we're going to say that at this point, this is going to be the point B, right? So y is equal to B when x is A. So now if we want to know this area, our first approximation, like when we were trying to work with gradients, we drew a triangle and then used our knowledge of how to calculate the gradient of a straight line. So if we just say, well, it kind of looks like a rectangle as a starting point. So we've got this big rectangle, which has area AB. So if I say rectangle area equals A times B. So that's our first estimate for the area. It's not very accurate because we can see that there are some bits, there's more above the line than there is below the line. So it's definitely we are underestimating the area, but it's a first attempt. Now, what did we do last time to make our estimate more accurate? We considered H1 and H2. And how did we modify them to make our second estimate better? Perfect, thank you, GR. We moved them closer. So we can do the same here. So rather than taking our rectangle as the whole thing, we could have instead said, well, if I take it as this rectangle here, plus this rectangle here, plus this last bit, so that would be the same one, right? So then you go under there. Okay, so now I've drawn a slightly different estimate. So then you could calculate the area of this one, right? Area 1, which is a rectangle. Area 2 for this rectangle. And then area 3. Okay, turns out that would actually be a slightly estimate because of how I've drawn them. It isn't exactly ideal. So let's split this one up and make it better, eh? Let's do, suppose we went to, let's do that. And then let's do the last one there. So this is area 4 and this is area 3. So now we've just got 4 rectangles and we can reasonably straightforward work out those areas. So if we said this was at, let's say A over 4, suppose that was A over 2 and that was 3A over 4. Okay, so we split it up into 4 equal parts. And now each of them gives you, I am the guy for number file, yes. It then gives you the total area of 4 rectangles all added together. So we've got 4 rectangles, and that's going to be, well, who knows? We get some answer, and it's slightly better, right? So we've improved our estimate. Instead of having one giant rectangle, thanks, Edu Ninja. So instead of having one giant rectangle, we've split it up now into 4 smaller rectangles, and we've got a better answer. So what do we do next to get an even better approximation for the area? Exactly, make more rectangles. So we want to make the rectangles even smaller. So at the moment, I've made them all 1/4 of the distance. So if I then made them all 1/8 of the distance, and went up to here, and then this one up to here, and then split this one in half, split this one in half, and that one, and then split this one in half. So we split them all up. And what we're doing is, I rub this, well, I don't need that anymore, do I? So what we're doing is we're making them smaller and smaller, and the area at each step is equal to the width, which is, from how I've drawn it, let's say h over n. And then it's multiplied by the height. So the height, this is between 0 and a over 8. And I'm taking the height here to be y equals f at the point a over 8. So it's h over n times the height, which is f at that point at h over n. So that would give me the rectangle at one particular, actually, I'll use A considering I wrote A. So this is now true. And we've done an example when n equals 8. Let me just think about how I want to do this. So it's that times capital N. And then, right, I'm going to rewrite this out, make it clear. So what we've got is the area of the first one is equal to 0 to a over 8. So that's a over 8 times the height, which is f at a over 8. And then we add on the area of the second rectangle. So that's going to be between a over 4 and a over 8. So 1/4 minus 1/8 gives us 1/8. So this now gives us a over 8 is the width, and the height is f at a over 4 times f a over 4. And then the next one is going to have a width of a over 8 times f at a over 2. No, a at 3/8. And then this carries on all the way up until the last one. So there are 8 different terms in this sum. So what we can do is we can simplify it and write it as one big sum. So this is just equal to a over 8 times the sum from, so if I write that as an 8 and that as a 2, the sum of k a over 8, where k is equal to 1 up to 8. Okay, so we now have this formula for our area when we use 8 rectangles. Now, if I went back and changed this to 16 rectangles, I divided them all in half again, then now what we're going to do is replace the 8 by 16 because they're all half smaller. This gets replaced by 16, and this number on the top gets replaced by 16. So if we're trying to write down a general formula for this, we're going to keep making these smaller and smaller and smaller. So if we write down a general formula, wherever I've just replaced an 8 with a 16, let's call that some number n, right? And then we're going to let n get larger and larger and larger. Because if we let this number, we started with it at 2, then 4, then 8, then 16, and we got a better and better approximation for the area by making it into thinner and thinner strips. So if we do the same, so I'll keep the one at the bottom. So I've left the one at the bottom for your reference. So what we've got now is the area is equal to a over n times the sum from k equals 1 to n of ka over n, like that. And now, as I've just hinted at, we want to let n get larger and larger and larger. And so what we want to do is let n go to infinity. Because if n goes to infinity, it's getting bigger and bigger and bigger. What we're doing, n is the number of strips. So as we increase n, we're dividing this up into smaller and smaller strips. And so we get a better and better approximation for the area under the curve. So all we're doing are adding up loads of really, really thin rectangles. So if we now let n go to infinity, so the area is equal to the limit as n goes to infinity of this. And that is your formula for an integral. So we change the notation a little bit when we do the integral sign, but it's basically telling you exactly that. So this is, if you now take a function, you can plug this in. Oh, this is f of that. My apologies. So if you change your function f, so here I did this sort of wave-like sine function. So if you change your formula for f, you then just change in here. So you could do this, for example, with x squared if you want, and convince yourself you get 1/3 x cubed coming out in your formula. These ones are a bit harder than the differentiation. So the first one I talked through was differentiation from first principles, and this would be integration from first principles. The differentiation ones are a bit easier. So if you want practice with this kind of thing, try the differentiation one from sort of 20 minutes ago, half an hour ago in the stream. Try some of those questions with different functions f. And then if you want to move on to the integral one, you can try it with this formula, and it should work. Right, so that's about 1 hour and 3 minutes. It's a perfect time to stop. So thank you again, everyone, for joining me. I hope you've learned more about travel graphs. I hope you've learned a lot about differentiation and integration. I was not expecting to do a beginner's course calculus, but that's what we've ended up doing. But thank you for suggesting the questions. Edu Ninja, I'm doing this every Friday at 4 o'clock. So there is a schedule, and the same for everybody else. I'll be back in another week at 4 o'clock UK time doing this. In the meantime, if you want to keep sending me questions, that's absolutely fine. So the main focus of these videos is going, hello Brazil. The main focus of these videos is going to be on the videos I'm releasing on the Monday. So next Monday, the Tom Rocks Maths Appeal video is looking at the volume of 3D shapes. So cuboids and spheres and prisms and various things. So volume of 3D shapes, that video will come out on Monday. Then Bobby and Susan from Maths Appeal will answer your questions on Thursday. So make sure you've written your questions in the comments or posted them to me on social media by Wednesday to give them a chance to prepare their answers. And then I'll be live next Friday, 4 p.m. UK time. So again, I'll start with questions based on 3D shapes and based on volumes. And then if you have other questions, I'll take them in the live chat. But if you also have questions now that you really want to ask, so I know someone's mentioned they have a question, if you put it in the comments, then I'll note it down and I'll start with that question also next week. Okay, right, awesome. So I'll see you all in a week. Thanks again. Bye-bye.